Now, in today's class, I am going to discuss about the three-phase transformer connections, and also we are going to discuss some numericals based on the three-phase transformer. But before moving to the three-phase transformer connection, I want to discuss something more about the star and delta. Okay, yes sir. So I am interested to discuss something more about the star and delta. Is it okay? Yes sir. So let's first discuss one question in order to make our three-phase understanding in a more better way. So let's have one question. Okay, please observe and please write this question. The three-phase generator is shown in figure below. The three-phase synchronous generator is shown in figure below. Okay, yes sir. So generator is feeding three-phase. Generator is feeding three-phase, or generator is feeding 320 ohm resistance, 320 ohm resistive load, 320 ohm resistive load. If the effective voltage induced in each phase if the effective voltage induced in each phase is 120 volts, calculate the following. First part shown below. Okay, shown in figure A, I am writing. Okay, in figure A. Now please observe here. Calculate the following. First part, the power dissipated in each resistor. The power dissipated in each resistor. This question is going to make you each and everything clear. Whatever doubt you have related to a three-phase system, that is going to be covered through this question. Please observe. The power dissipated in each resistor. Okay, sir. The power dissipated in three-phase load. The power dissipated in three-phase load. Third one, the peak power PM dissipated in each resistor and the last one, total three-phase power compared to PM. Total three-phase power compared to PM. It's an important one, so I have represented the entire question. You need to note it. A three-phase generator is shown in figure. I'm going to show you. Shown in figure A. In figure A, generator is feeding 320 ohm resistive load. If the effective voltage induced in each phase is 120 volt, calculate the following: power dissipated in each resistor, the power dissipated in three-phase load, peak power PM dissipated in each resistor, and total three-phase power compared to PM. Okay, compared to PM. Now please observe the figure given in this format. Let me show you the figure also. So figure is given in this format. So we have one phase, another phase, and another phase, and the resistances are connected in this fashion. Resistances are connected in this fashion. However, it's a part of a network, but I know it needs to be understood before we are going to the three-phase system. So, in the figure it is given that this is your EA, induced EMF EA, induced EMF EB, and induced EMF EC. We have a resistance R, and R. Now, this is your figure A. All the resistance are of 30 ohm. All the resistance are of 30 ohm. We all know that, sir, we have three identical phases, AA dash, BB dash, and CC dash, and we have a DC field onto the rotor, and this DC field onto the rotor is rotated. So we have an induced EMF A phase plus B phase plus C phase. Each resistances are of 20 ohm. Okay, it's given as 20. Kindly correct it. 20 ohm. So each resistances are of 20 ohm. Let's make it 20 ohm. Okay. So each resistance is R of 20 ohm. This is the figure given. Please observe, please observe. Great question, please observe. Let's have a discussion on this question. Let's have a discussion on this question. Okay. Yes. Sir, three generators as shown in figure. A three-phase generator as shown in figure A. Generator is feeding 320 ohm resistive load. If the effective voltage induced in each phase is 120 volts, it means voltage across each phase is 120 volts. All the phases are identical, so voltage across each phase is 120 volts. Yes, sir. Now, I am interested to calculate the power dissipated in each resistor. Please tell me what is the power dissipation in each resistor. That is very easy part. Can you find the power dissipation in each resistor? Can you find the power dissipated in each resistor? Power dissipated in each resistor. Power dissipated in each resistor. Can you find the power dissipated in each resistor? Sir, power dissipated in each resistor. So first part is power dissipated in each resistor. So what is power dissipated in each resistor? Sir, power is equals to EA square, or you can say, sir, induced EMF square by R. So this will be equals to 120 square by 20, 720 watts. Hoping all of you are aware with this. Yes, sir. Yes, sir. Up to this part, it is absolutely fine. What is the next part? We need to find the power dissipation in each resistor, then the power dissipation in a three-phase load. So what is the power dissipation in three-phase load? Sir, total three-phase power. So what is total three-phase power, sir? 720 into 3. Can I do that? Yes, sir. So you can easily find it out, sir. 720 into 3, that is 2160 watt. So what is power dissipation in a three-phase load, across three-phase load? So what is power dissipation in a three-phase load? So sir, we have a power dissipation in a three-phase load as second part, power dissipation in three-phase load. So what is power dissipation in three-phase load, sir? Power dissipation in three-phase load is 3 times of power dissipation across each resistance. Yes, sir. So three-phase power, that is 3 into 720. So you can write 2160 watts. Hoping up to this part everything is clear. Hoping up to this part everything is clear. Yes, sir. Great. Very easy, sir. Up to this part very easy, sir. Now we need to find the peak power dissipated in each resistor. So what is peak power dissipated in each resistor? I am interested to know about the peak power dissipated in each resistor. Peak power dissipated in each resistor. Peak power dissipated in each resistor, sir, is PM, and PM can be represented as, I have represented it as PM. So PM can be represented as peak power is, sir, peak voltage square, peak voltage square by R. Yes, sir. What is peak voltage, sir? Root 2 times of the maximum voltage, sir. So root 2 times square of the maximum into R. We know about the maximum power because the maximum voltage, RMS value is given to you. RMS value is given to you, sir. So RMS value is defined as maximum value upon root 2. So one can easily write root 2 times of ERMS. Now RMS value is the effective value. So sir, this will become twice of, please observe here, this will become twice of, please observe, twice of RMS square. RMS is 120 square by RC, R is equals to 20. So it means 720 into 2. Can I say this? Yes, sir. So 1 peak power loss will become sir 720 into 2, 1440 watts. Are you able to understand this? Can you find the peak current, peak voltage and everything? Yes, sir. Already we are able to observe the peak voltage, sir. Peak voltage is root 2 times of the RMS voltage. And if we need to find peak current, then peak current will be equals to ERMS by R. So now we know about the peak current across each resistor, peak power across each resistor. So we have peak power dissipated across each resistor. It can be observed here, peak power dissipated is 1440 watts. But what is the actual power dissipated across each resistor? Actual power dissipated across each resistor is just 720 watt. Is it okay? Yes, sir. So peak power is Sir, peak power is 1440 watt. Next part is total three-phase power compared to PM. Now I am interested to calculate total three-phase power compared to PM. Total three-phase power compared to PM. So the ratio of PT by PM. Can you calculate the ratio of PT by PM? Yes, sir. D option is, D part is PT by PM. So PT is the total three-phase power. Yes, sir. Dissipated across the load 2160 by peak power is 1440 watts. Yes, sir. Nearly 1.5 times. Sir, this ratio is 2160 by 1440. So 1.5. Is it okay? Yes, sir. So now we have different parts. Now please observe here. I am going to change a little bit with the figure. I am going to change the figure. Please observe. We have the values. Are you satisfied with the solution? Are you satisfied with the solution up to this part? Anything, any doubt? Yes, sir. Now I am going to change it a little bit. Yes, sir. I am going to change it a little bit. Please observe here. Sir, can I represent this figure? Please observe here. Sir, can I represent this figure? Sir, can I represent this figure in this way? Where we have EA, EB and EC as the effective value across AA dash, BB dash and CC dash, and effective current across the resistors of 20 ohm is IA, IB and IC. Now please observe, please try to understand why I have represented in this way. Sir, basically EA, EB and EC are 120-degree displaced in time, and that time is the time taken by this rotor to change its position. At this particular position, induced EMF at A is maximum. At this particular position, induced EMF at C is maximum, and at this particular position, induced EMF across B is maximum. So induced EMFs are being displaced in time by 120 degree. Yes, sir. So induced EMFs are being displaced in time by 120 degree. It means EA, EB and EC are being displaced in time by 120 degree. Yes, sir. You can represent in this way. Please observe. EA, EB and EC are being displaced in time by 120 degree. Yes, sir. Each will have a same peak value of the voltage. Already we have calculated the peak value. Yes, sir. 1, 2, 3, 4, 5, 6 and 7 we have. Okay. Now please observe here. Already yesterday we have observed induced EMF EA, EB and EC are being displaced in time by 120 degree, and that time depends upon the sir, speed of rotation, and that time depends upon the speed of rotation. Yes, sir. Let us suppose we have the phase sequence as A, B, C. Phase sequence depends upon the direction of rotation of the rotor. So we have EA. Suppose we have EA, EB, and EA, EC, and EB. Okay. EA, EC, and EB. So I'm representing EB here. Yes, sir. EA, EB, and EC. So these voltages divided by these peak voltages, if these voltages are a peak voltages, if these voltages are a peak voltages, if these voltages are a peak voltages, half of the maximum, half of the peak, and 0 minus half of the peak and minus peak. Yes, sir. So these peak voltages divided by resistance, they are going to create a peak current. Yes, sir. Since it's a pure resistance, so it can be analyzed here, sir. If VA at an angle 0 divided by R, then we have IA at an angle 0 only. Voltage and current are going to be in same phase if a resistive load is connected. Yes, sir. So IA, IB, and IC, the currents created here, IA, IB, and IC. So I am interested in IA, IB, and IC. So in this circuit, it can be clearly observed. IA is equals to EA by R. IB is equals to EB by R. IC is equals to EC by R. Since EA, EB, and EC peak magnitudes are same, so EA, EB, and IA, IB, and IC peak currents are also in the same phase. But peak currents are also in the same phase, but they are displaced in time with each other. Is it okay? Yes, sir. So I can represent here. This will be your IA, IC, and IB. Can I represent in this way? IA, IC, IB. Yes, sir. So what are the peak currents and what are the peak voltage? Sir, peak voltage is equals to root 2 times of RMS value, that is effective value. And what is root 2 times effective value, sir? It will be equals to under root 2 times of effective value is given to you, that is 120 volt effective. So 120 volt. So we have peak voltage and we have peak current also. What is the value of peak current, sir? The value of peak current will become root 2 times of the maximum current, and maximum effective current is 120 by R is of 20 ohm. Yes, sir. So R is of 20 ohm. So we know about the effective current. Effective current multiplied by root 2 will give you the peak current, that is maximum current, also called as maximum magnitude of the voltage or maximum magnitude of the current. So that will be equals to sir 120 into root 2, you can write 169.70, and divided by 20, you can write, sir, 8.4852 ampere. So now we know about the voltage and current. So the wave shape of the voltage and current is of this type. Are you satisfied? Yes, sir. In this figure, EA is going to be maximum after 120 degree time. EC is going to be maximum after 120 degree in time. EB is going to be maximum. So the current flowing in the resistive load IA, IB, and IC are also being displaced in time by 120 degrees. Is it okay? Yes, sir. So can you find the peak power? Peak power across each resistor. What is peak power, sir? What is peak power, sir? Sir, peak power is EM into IM. So sir, EM into IM means 169.70 into 8452. Please calculate peak power. So peak power will become 169.70. Sir, this will be 140 1440 watts. Sir, it matches with the previous calculation. It matches with the previous calculation that we have represented here. Please observe what is the peak power dissipated in the resistor. Sir, the peak power dissipated in the resistor is 1440. And now in this circuit you can observe what is peak power, sir. Peak power in this circuit is also 1440 watts. Is it okay? Yes, sir. Is it okay? Yes, sir. What is the three-phase power? What is the three-phase power? What is the three-phase power taken by this circuit? Please see. This is the peak power. What is three-phase power taken by this circuit? So three-phase power taken by this circuit is, sir, RMS value of the voltage into RMS value of the current. Can I represent in that way? Yes, sir. Okay, sir, what about the return path, sir? Why you haven't represented a return path? Why that path is not needed, sir? Why you are not representing a return path, sir? Why that path is not needed, sir? IB can be represented here. Why that third path you haven't represented, sir? What about the return path, sir? Can you find the current at any instant? Can you find the current at any instant through these three lines? Now let's have a discussion over the current flowing through these three lines. Okay, please see. We have a IA 0 degree, 60 degree, 120 degree. Please observe. We have IA 0 degree, 60 degree, 120 degree, 180 degree, 240 degree, 300 degree and 360 degree. Is it okay? Yes, sir. Same, we have voltage also 0 degree, 60 degree, 120 degree, 180 degree, 240 degree, 300 degree and 360 degree. Is it okay? Yes, sir. Can you find what is IA plus IB plus IC? Can you find what is IA plus IB plus IC at any instant? We have 7 different instant. Let it be instant 1, instant 2, instant 3, instant 4, instant 5, instant 6 and instant 7. Now let's find out the value of the current at any instant. What is the value of current at any instant? IA plus IB plus IC. Can you find what is the value of IA plus IB plus IC? Can you find what is the value of IA plus IB plus IC at instant 1? Sir, IA is maximum value. IB is minus half of the maximum. And what is IC? IC is minus half of the maximum. So what is the net value of the current at instant 1? IA plus IB plus IC. Sir, you are saying if this current is flowing, it means IA is flowing peak. Okay. So IA is flowing peak. IA is flowing peak. Okay. When IA is at peak, what about IB and IC? They are at minus half of the peak. Minus half of the peak means, sir, it goes in this way. Minus half of the peak means, sir, it goes in this way. Because if I have taken plus current coming from voltage to resistor, the negative current means it is going back. So it can be clearly observed from this circuit, when IA peak is coming here, at the same time what about IB? Half of the maximum and half of the maximum. If I am going to join all these points here, then sir, net current in the neutral link is a 0. Why, sir? Because if you are going to add IA plus IB plus IC at any instant, that will be equals to 0 only. If you are going to add IA plus IB plus IC at any instant, you can check it at instant 2, instant 3, instant 4, instant 5, instant 6. Yes, sir. So it can be clearly observed here that phasor sum of IA plus IB plus IC is equals to 0 at any instant. Since the phasor sum of these current is equals to 0, because they are equal in magnitude but are being displaced in time by 120 degree. Okay. Now please see. So sir, IA plus IB plus IC are equal in magnitude, but it is being displaced in time by 120 degree, and therefore you can say, sir, this neutral link does not required. In a three-phase system, you may eliminate this neutral link, sir. This neutral link is now not needed, sir. You can eliminate this neutral link, sir, because IA plus IB plus IC, it can be clearly observed at any instant is equals to 0. Is it okay? So let me show you here again. Now, please observe IA plus IB plus IC, IA plus IB plus IC, IA plus IB plus IC is equals to 0 at any instant. At any instant. Yes, sir. So since IA plus IB plus IC is equals to 0 at any instant, you can say, sir, we may neglect the neutral link, and electrical model can be represented directly in this format. Is it okay? Why we don't need a neutral? Why we don't need a neutral in a case of a balanced load? When the loads are of equal magnitude in a three-phase balanced supply, when a load are of equal magnitude in a three-phase balanced supply, then the load is called as a balanced three-phase load. Load is called as a balanced three-phase load. If the loads are equal, you can say, sir, the load is called as a balanced three-phase load. When a balanced three-phase load is supplied by a balanced three-phase source, the balanced three-phase source means the voltages are being displaced in time by 120 degree, but they are equal in magnitude. Then there will be no current flowing through the neutral link, and that is the greatest advantage of three-phase system. That is why we are using three-phase system. In case of one-phase system, how many wires are needed? In case of one-phase system, how many wires are needed? How many wires are needed? If we have only EA, we need two wires. One is ongoing, one is return. If we have a two-phase system, how many wires are needed? If we have no BC, that is not BC current, IA plus IB plus IC, IA plus IB plus IC current, IA plus IB plus IC current at any instant is equals to 0. See, if you are observing at instant 1, what is the current IA? Sir, at this particular time, IA is equals to peak value. But IB and IC at this particular time is minus of half of the peak. So what is the net current? Sir, plus peak minus half of the peak, minus half of the peak. So net is a 0. Now see, sir, a balanced three-phase source. Now we are able to understand what is called as a balanced three-phase source, balanced load. How many number of wires are needed for a two-phase system? How many number of wires are needed for a two-phase system? Can you tell me? How many number of wires are needed for a two-phase system? Sir, for a two-phase system, we need 1, 2, 3, 4 wires. 4 wires are needed for a two-phase system. And how many wires are needed for a three-phase system? Can you please tell me how many wires are needed for a three-phase system? Sir, if the system is a balanced, then we just need 3 wires. So this is also a reason behind a three-phase system to be preferred more than the two-phase system. Yes, sir. And what is the peak power, sir? What is the peak power? Let's conclude with the power. If we have only one phase system, then what is the power? If we have one phase system, then what is the power, sir? Let's talk about from one phase system. Okay. Consider AA dash connected with R. Consider AA dash connected with R. Okay. Now please observe. I am going to show you one very important thing again in a note point. Okay. Please observe here. Consider a one phase system. One phase system. So in a one phase system, you can say, sir, we have a resistance R and a EA. Let us suppose in this way, this EA effective value is 120 and resistance R is 20 and current I is flowing. What is the nature of this EA? Sir, AC, single phase AC. So a single phase AC can be represented here. A single phase AC can be represented here in this way. Sir, this will be your voltage. Let us suppose this will be your voltage. Voltage Vm sine omega t. So if Vm sine omega t is the voltage, what is the current, sir? What is the current, sir? Current, sir. What is the current, sir? Current is, sir, current is Im sine omega t. Yes, sir. Current is Im sine omega t. Im sine omega t. Let me represent a co-sinusoidal waveform with a rotor also. Okay. So I'm going to show you with a rotor. Let us suppose we have a rotor here. I have a single phase generator. I'm comparing a single phase generator with a two phase generator and a three phase generator. To understand why we are interested in a three phase instead of single phase or a two phase system, please observe. Suppose we have this to be A dash, okay, A dash, okay, sir, and I have this as a pole, okay, yes, sir. I'm going to rotate this pole inside the rotor. At this particular instant, what is flux? Flux is maximum. On a reference axis, you can represent a time phasor. In a time phasor, you can represent any parameter as a reference. So presently, I am taking field axis as a reference. Is it okay? So this is your reference axis. Yes, sir. At this particular time, there will be no induced DMF. Onto A and A dash. Why? Because, sir, A and A dash presently are in such a position that magnetic line of force is moving parallel to the conductor, and therefore from BLV sine theta, induced DMF is 0. When it reaches here after 90 degree, then induced DMF will be maximum. So let's take this instant as a reference instant. Okay, this instant as the first instant. So at omega t is equals to 0, we have a V maximum. Then after 90 degree, sir, it will reaches to. Sir, after 90 degree, it will reaches to. Please see. Sir, after 90 degree of rotation, it will be reaches to. Please observe. Presently it is here. This will be the position, and after 90 degree, this will be the position. At this particular position, again the induced DMF is 0, and after 180 degree, it will reaches to. After 180 degree of rotation, it will reaches to here. Now induced DMF across A dash is again maximum, but the polarity is being reversed. Yes, sir. So after 180 degree, you can say polarity is being reversed. Is it okay? Yes, sir. Then again, same. So one can easily represent the induced DMF in a single phase machine. Okay? Yes, sir. So we have an induced DMF in a single phase. What is current? Current will become E by R. So current E by R, it means current is in phase with the voltage. Please try to understand here. Sir, we have Vm cos omega t. So for Vm cos omega t, we have Im cos omega t, because a resistive load means, sir, once again represent, okay, same thing. Please observe, it's a single phase system. Presently I am representing a single phase. So a single phase alternator will have an induced DMF this. The frequency of induced DMF depends upon the speed of rotation. We all know that. Yes, sir. It depends upon the speed of rotation. If you are completing one rotation in time period t, then frequency of voltage is equals to 1 by t, that is F. Okay, yes, sir. And current Im sin omega t is Im cos omega t, because voltage divided by resistance is not going to change in phase. Yes, sir. So what about the power? Sir, power will become, it can be observed here. We can multiply V and I. If I am going to multiply V and I, it will become V cos omega t into I cos omega t. Yes, sir. V cos omega t into I cos omega t. Yes, sir. So the multiplication of these two will be reaches here. Then again, it will be reaches here. Can I represent in this way? Yes, sir. So we have a power. We have a power. What is peak value of the power? Sir, Vm into Im. What is the peak value of the power? Vm into Im is the peak power. Yes, sir. But what is the effective value of the power? Sir, effective value of the power is Vrms into Irms. So what is the effective value of the power? You can easily observe here that effective value of the power is maximum by 2. Can I say this? Yes, sir. What is RMS value? Maximum by root 2, sir, and maximum by root 2, sir. So, sir, maximum by 2. Sir, single phase can generate power PM. But what is the effective power we are getting from a single phase generator? Sir, PM by 2. The peak power it can generate PM, but we are getting just PM by 2. The peak power it can generate is PM, but the effective power we are getting just PM by 2 only. Effective power is Vrms into Irms, effective voltage into effective current. Yes, sir. Instead of having one phase, let's suppose we have a two-phase system. So what happened if we have a two-phase system? Please observe. In case if we have a two-phase system, then two-phase system is said to be a balanced two-phase system if the phases are being displaced in space by 90 degree. So in a two-phase system, the phases are being displaced in space by 90 degree. Is it okay? Yes, sir. The phases are being displaced in space by 90 degree. In a two-phase system, the phases are being displaced in space by 90 degree. If both have resistance R and resistance R, AA and EB. Yes, sir. So now if you observe IA and IB, in a balanced two-phase system, when I'm saying balanced two-phase system, it means, sir, both A phase and B phase are identical, but they are displaced in space by 90 degree. It means AA dash and BB dash are being displaced in space by 90 degree. Yes, sir. AA dash and BB dash are being displaced in space by 90 degree. Suppose if we have a two-pole machine. Then this will be a two-pole rotor. Is it okay? Yes, sir. If we have a four-pole rotor, you can represent the four-pole rotor accordingly. Now please observe here. After 45 degree, what happened, sir? A comes to the magnetic neutral axis. However, at the same time, B comes to the maximum north. Can I say this? Sir, after 90 degree of rotation, it's a two-phase system, sorry. For a two-phase system, a two-pole I am representing here. Let's suppose a two-pole system. Two-pole I am representing here. So presently AA dash is maximum. So for AA dash is maximum, we are getting same thing. But after 90 degree of rotation, what happened, sir? After 90 degree of rotation, we are getting BB dash maximum, sir. After 90 degree of rotation, we are getting BB dash maximum, sir. Please observe here. So we have EA in a two-phase and EB in a two-phase. Now we have two phases, A and B. So, sir, EA is maximum at this point, and after 90 degree of rotation, north and south will be in the position such that the induced EMF onto the B and B dash will be maximum. Yes, sir. Let's have this to be B and this to be B dash. Okay. Yes, sir. And we are rotating in this direction. So, sir, we have B phase voltage and current can be represented with this. Yes, sir. This will be your B phase induced EMF. If A phase is cos omega t induced EMF, then 90 degree displaced is your B phase. So B phase will become cos omega t plus 90, so that will become sin omega t. Is it okay? Yes, sir. And its current is also in the same phase. Its current is also in the same phase. Current is also in the same phase. So what is the product of voltage and current? What is the product of voltage and current in a two-phase system? Please observe. What is the product of voltage and current in a two-phase system? Sir, the product of voltage and current, here it is maximum, and after 90 degree it is again maximum. After 90 degree it is again maximum because of EA-IA, and after 90 degree because of EB-IB it is maximum. So this will be your EB-IB. EB and IB. Is it okay? Yes, sir. And here I am representing VA and or EA and IA. So it can be clearly observed, sir, that what will be the power? Sir, power will become twice of power will become, sir, power will become Vm into Im. That is peak power. Yes, sir. And if you observe the peak power and effective power, so what is the effective power in a two-phase system? Sir, effective power in a two-phase system is twice of Vrms into Irms of per phase. Yes, sir. So what is Vrms of per phase? Sir, that will be equals to Em by root 2 into Im by root 2. So this will become Pm by 2 Pm by 2, that is Pm, sir. Great, sir. So if we are going to use a two-phase system, then comparative to a single phase system, your effective power is increased considerably. Previously, what is your effective power, sir? Previously, in a single phase system, our effective power is Pm by 2. And what is maximum power? Maximum power is the peak. What is the peak power? Peak power is the Vm into Im. So, sir, the generator is capable to create a peak power of Vm Im. But the effective power available for the load is, sir, Pm by 2 in case of single phase. In case of two phase, we found a great thing. The peak power that generator can generate is equals to VMIM, that is peak power VMIM, and the effective power generated by the two-phase generator is also PM. So it means two-phase will have a better power generation comparative to a single phase. Is it okay? Are you able to understand this? Yes, sir. But how many number of wires are needed? 4. And when we talk about a three-phase system, then with the three different wires, we don't know 6 wires. We don't needed 6 wires. We just needed 3 wires to do the balanced load supply. And how much power it is going to supply? Sir, it is going to supply 1.5 times of the peak power. PM is the peak power, PT is the effective power. So it means, sir, PM is the peak power and effective power is PT. So effective power that a three-phase synchronous generator can supply is equals to 1.5 times of the peak power. If we have used the 3 single phase transformers, then we will get, sir, PM by 2 plus PM by 2 plus PM by 2. We will get only PM by 2 plus PM by 2 plus PM by 2. It means 3 PM by 2. Is it okay? Yes, sir. And we need 6 wires. But in a 3-phase system, we just need 3 wires and the same amount of power is being transferred. Gautam, Ash, are you able to understand this part? Please tell me, are you able to understand the greatness of 3-phase system? What is with the single phase system, sir? There is a problem with the single phase system, sir. Its peak power and effective power is different. Two phase system better than the single phase system, sir. Peak power and effective power is same. But the number of wires needed is 4. With the same 3-phase 4-wire, we are capable of same rating. Same rating 3-phase 4-wire. 3-phase 4-wire. With the same 3-phase 4-wire, same rating 3-phase 4-wire. As in case of a 2-phase, we are capable to deliver 1.5 times of the maximum power. 1.5 times of the peak power of single phase. Is it okay? Yes, sir. Yes, sir. 1.5 times of the 1.5 times of the peak power. 1.5 times of the peak power. Is it okay? So we will prefer to go by the 3-phase system because of this main advantage. Hoping you are able to understand up to this part. Now we have a great clarity related to a 3-phase system. Come to the star and delta. Next, come to the star and delta. If you want to ask anything, please feel free to ask. Okay. Let's discuss about star. So our 3-phase system may be a star connected system or it can be a delta connected system. Let us first discuss about the star connected system. Star connected means A phase, B phase and C phase are being displaced. The voltages in A phase, B phase and C phase are being displaced in time by 120 degree. Let us suppose we have a star connected system and this star connected generator is feeding to a balanced 3-phase balanced unity power factor load. Is it okay? Yes, sir. So please observe here, we have EA, we have EB and we have EC. Unity power factor. Now please observe here. Sir, IA is EA by resistive load because of unity power factor. Power factor is always on basis of per phase. Okay. Yes, sir. So it can be clearly observed here. IA, IB and IC are in phase with EA, EB and EC. Is it okay? Yes, sir. So how to represent? Please observe here. Voltages VA, VB and VC are being displaced in time by 120 degree. Let us suppose we have a phase sequence as A phase, C phase and B phase. What is the phase sequence, sir? Sir, we have a phase sequence. We have phase sequence A, B, A, C, B. Okay, yes, sir. Because always being stationary and observe the phasor to be rotating in an anti-clockwise direction, observe which phasor will come first peak in front of your eye. Yes, sir. Now please observe. For a unity power factor current is also in phase with a voltage. Okay, sir. Now please observe. I am interested to calculate line to line voltage. The voltage which is appeared across the windings are said to be phase voltage, and the voltage across the line to line is called as a line voltage. So here this voltage is called as phase voltage and this voltage is called as line voltage. Is it okay? Yes, sir. Now please observe here. Sir, how to calculate line to line voltage? How to calculate line to line voltage? Sir, I am interested to calculate VAC. What is the value of VAC, sir? VA minus VC. Is it okay? Yes, sir. So VA minus VC can be represented here. VC is this, then minus VC can be represented here. Please see. Minus VC can be represented here, sir. And minus VC, minus VA minus VC can be represented by a simple parallelogram method. Yes, sir. So it can be represented by a simple parallelogram method. Yes, sir. So one can say, sir, we have VCA, we have VCA, VAC, VAC can be represented in this way. Yes, sir. Now please observe what is the angle here. This angle is 120 because the voltages are being displaced in time by 120, and this time depends upon the time taken by the generator to rotate from A phase to C phase. That time is called as a 120 degree time. Okay. Yes, sir. Now what is this angle? This angle will be 60 degree. Okay, sir. And the phasor sum of VA and minus VC will become. The phasor sum of VA and minus VC will become. Please observe here. Please observe here. What is the phasor sum, sir? Whenever we have to calculate a phasor sum between two phasors, then phasor sum will be equals to A phase magnitude square, C phase magnitude square plus of angle between A phase and minus of CA between the two phasors. So what is the angle between the two phasors? Sir, the angle between the two phasors for which we are using to calculate the phasor sum is a 60 degree. Okay. Yes, sir. Now please observe here. Sir, VAB is the line voltage. So I am writing VAB as root over of. Let all the phases are identical. So for a balanced supply, we can say VA is equals to VB is equals to VC. Let it be phase voltage. Yes, sir. So this will become phase voltage square plus phase voltage square plus twice of phase voltage square cos of 60 degree. You can take V phase as a common. Yes, sir. And you can write, sir, root over of twice of 1 plus cos alpha, or you can say cos 60. Or you may write it in terms of alpha also. Is it okay? Yes, sir. Alpha is 60 degree. So what is 1 plus cos alpha? 1 plus cos alpha is 2 cos square alpha by 2. So for 2 cos square alpha by 2, you will get phase voltage into root 2 into cos of alpha by 2. What is the value of alpha here, sir? Alpha is sir 60 degree. That is the angle between VA and VC. Whenever we have to perform a phasor addition, we always do a phasor subtraction. We always refer arrow tip to arrow tail, and we can use a parallelogram method. Is it okay? Yes, sir. So what is the angle, sir? Cos of 60 by 2, that is 30. Cos 30 means root 3 by 2, sir. So this will become root 3 VPH, sir. It means what is the line voltage? Line to line voltage we are observing. Magnitude, the line to line voltage is root 3 times of phase voltage in case of star connected load. What is line current? Sir, the current which is supplied through the line. And what is phase current? Sir, phase current is the winding current flowing in the windings of the transformer or the windings of the machine or windings of the phase. So it can be observed here that, sir, phase current and line current are same. So in case of star connection, always remember phase current and line current are same, but the line voltage is root 3 times of the phase voltage. Sir, omega t is positive and negative sequence shows to identify. See, if the phase sequence is ABC, then negative phase sequence is ACB. Later on, during unbalancing, we will see what about the negative phase sequence. What are the negative phase sequence? Okay. Presently, just focused on to the phase sequence which I am telling you. Okay, sir. Now we have a line voltage. What is line voltage, sir? Line voltage is root 3 times of the phase voltage. Yes, sir. Suppose we have to calculate line to line voltage between BC. So how to calculate the line to line voltage between BC? Sir, you can write VCB, and VCB can be represented as VCA. VCB can be represented as VC minus VB, and VC minus VB can be represented here. So this will be your line to line voltage VCB. Is it okay? That is VC minus VB. Yes, sir. Please observe, what is the angle between the line to line voltages in time? So if you observe a time displacement, sir, this is 60, so that represents 30. Yes, sir. And this is 90, sir. So 30 plus 90, so this will also be displaced by 120 degree. So not only phase voltages are being displaced in time by 120 degree, as well as line voltages are also displaced in time by 120 degree. Further, you can also calculate VBA. What is the value of VBA? VBA will be equals to VA minus VB. VB minus VA. VBA is VB minus VA. So VBA can be calculated here in this manner. Yes, sir. Yes, sir. So we have this as a line to line voltage VBA. So line to line voltage VBA, VBC, VCB and VAC are being displaced in time by 120 degree. Is it okay? Yes, sir. Now we are able to understand about the star. So in case of a star, sir, line voltages and phase voltages are being displaced in time by 120 degree. Line voltages and phase voltages are being displaced in time by 120 degree. However, line current and phase current are same. Whenever you are saying star, it means voltage across the winding is the phase winding and the current flowing through the winding is called as a phase current. Is it okay? Up to this part, everything is clear. So now we have a star connected system. In a transformer, there are two possibilities of this star. It may be a source side or it may be a load side. So I am just considering from a source side, and source side overview I have given to you. Is it okay? Up to this part? Yes, sir. Let's have a discussion of delta connected system also. Let's talk about delta system also. Then we will go towards the three-phase transformer. It's a part of a three-phase basic circuits. So now please observe delta and let me know if you are able to understand it properly. In case of a delta connected system, suppose I have a source side delta. So AA dash, BB dash, CC dash. Okay. Suppose our generator itself is connected in delta and it is supplying three-phase balanced load at unity power factor. So when I am saying three-phase balanced load at unity power factor, then it indicates, sir, current, line current and load voltage are in same phase. Okay, yes, sir. Let's talk about phase current. Phase current is the current that flows through the windings of the machine. Phase current is the current which flows in the windings of the machine. Sir, when A phase voltage will be maximum, then A phase current comes into the picture. Yes, sir. When A phase current is maximum, A phase will come into the picture. Then when B phase voltage is maximum, B phase current will comes into the picture. And when C phase induced EMF is maximum, then C phase current will flows and we can say C phase comes into the picture. Now please observe what is phase voltage. Phase voltage is the voltage across the winding. So this is your phase voltage. Yes, sir. And what is line voltage, sir? Between one line to another line. So this is also a line voltage. So in case of delta, it can be clearly observed that phase voltage and line voltage are same. Phase voltage and line voltage are same. You can observe the voltage between A line to B line or from A line to C line. A line to C line is the line voltage and voltage across A to A1 is the A phase voltage. Is it okay? Yes, sir. So for delta, line voltage and phase voltage are same. But what about current? Sir, for a unity power factor, let us take this IA as a reference. Okay. So this IA I am representing here the current flowing in winding A2 A1 is a reference. Then after 120 degree, when B phase will be maximum, then B phase current will be maximum, that is I B2 B1. Since voltage is being 120 degree displaced from A phase voltage, so current I B2 B1 is also displaced 120 degree in time from A2 A1 current. Similarly, your C2 C1 can be represented here. I C2 C1. Can I represent in this way? Please tell me. Yes, sir. Now please observe. These are the phase current. In case of balanced load, already in the first numerical of this class, we have observed in case of balanced load, the current magnitudes are equal. Yes, sir. So I am representing here, sir, I A2 A1 is equals to I B2 B1 is equals to I C2 C1. Can I say this? Yes, sir. I A2 A1 is equals to I B2 B1 is equals to I C2 C1. Let it be phase current IPH. They are equal in magnitude but displaced in time by 120 degree. Yes, sir. Further, what is the value of IA? It can be clearly observed by KCL at this point that current coming is IA2A1 and current going is IB2B1. So sir, IA phase current is the phasor sum of IL of A phase. Yeah, that is line current of A phase is the phasor sum of sum of minus of IB2B1 and IA2A1. So by parallelogram method, we can find this line current. This is what we call line current, and you can represent it as IA. What is the value of IA, sir? IA will become equals to root over of phase current of A2A1 plus phase current B2B1 plus twice of A2A1 B2B1 into cos of angle between them. So what is cos of angle between them? Sir, 60 degree. This angle is 60 degree, sir. Is it okay? Yes, sir. Now further you can say, sir, this angle will be equals to 30 degree. And what is the value, sir? It can be observed here. Sir, I phase into root 3. Yes, sir. After solving, we have root 3 times of phase current. It means line current in case of delta connected system is root 3 times of phase current. So in case of delta, we have line current and phase current having relation root 3 times. However, in case of a star, line voltage and phase voltages carries relation of root 3. Is it okay? Yes, sir. Further, if you want to calculate IB, what is the value of IB? Sir, IB will be equals to IB2B1 minus IC2C1. So IB2B1 minus IC2C1. Sir, this will be your IB. Is it okay? Yes, sir. And similarly, what is the current? IC current is this one, sir. So the current IC current will be IC2C1 minus IA2A1. IC2C1 minus IA2A1. So IC2C1 minus IA2A1. It can be clearly observed. This will be the line current. So sir, now we know about the line voltage and line current in case of star and delta properly. What is the angle difference between the line to line? So the angle difference between the line to line is again equals to 120. The angle difference between the line to line is again 120, sir. So the line voltages, line currents are also displaced by 120 degree from the phase current. I have considered delta as a source. When we treat delta as a source or delta as a load, they have a different line. It may lag 30 degree or it may lead 30 degree. If you are using as a source, we are observing it is lagging, it is leading by 30 degree from phase current. However, when it is acting as a load, that is going to be lag by 30 degree from a phase current. Okay, yes sir. So now up to this part, hoping everything is clear. Yes sir. So now we know about the star and delta. We also know about the single phase and three phase system. Why we are not interested in a two phase and why we are not interested in a single phase, now we know. The peak power that a single phase can give is equals to PM, and the peak power that a two phase that can give is equals to PM by 2 for a single phase, 2 PM for a two phase, and 1.5 PM for a three phase. But the greatest advantage is with the less number of wires, we can do a three phase transmission. And the greatest thing is if all the three currents are equal and they are displaced in time by 120 degree, then their net magnetic effect around the transmission will be zero. Net magnetic effect around the transmission will be zero. Sir, net magnetic effect around the transmission will be zero means, see, since the currents are being displaced in time by 120 degree. So this IA, IB and IC are being displaced in time by 120 degree. If IA, IB, IC are being displaced in time by 120 degree, if they are producing flux, because if the current flows through a wire, it will create flux. So they are going to produce a flux phi A, phi B, phi C. What is the sum of a current at any instant? Zero, sir. IA plus IB plus IC is zero. Similarly, the flux created by IA plus IB plus IC is also zero. Yes, sir. So it means a three phase system will have a better regulation possible. Is it okay? Net magnetic effect of the three phases is zero. Let's have a discussion on a three phase transformer connection, also called as a vector groups of a three phase transformer. We can connect a three phase transformer in two different ways. First one is a single unit of three phase transformer. Single unit of three phase transformer. Single unit of three phase transformer. In a single unit of three phase transformer, all three phases are wounded onto the same core on different limbs. So we have A2A1 A phase HV side and small A2A1 A phase LV side. Capital B2B1 B phase HV side, small B2B1 B phase LV side. Capital C2C1 C phase HV side and small C2C1 C phase LV side. Now we can connect these windings in our desired configuration. Suppose my desired configuration is star star zero connection. Suppose my desired configuration is star star zero connection. What is this star star zero connection? Soon I am coming. Please see. Please try to understand. Whatever I am saying, just listen. Sir, suppose we are interested to connect in a star star connection. So for a star star connection, I am going to short this A1, B1 and C1 capital, providing one neutral, and similarly small A1, small B1 and small C1 are being shorted. One neutral is provided on LV side also. Okay, sir. Now we have output terminal A2, B2 and C2 available for the HV side, and we have A1, small a2, small b2 and small c2 is the output of LV side, output terminals of LV side. Now the given connection will act as a single unit of star star 0 connection. HV side is represented as capital A, capital B, capital C, and LV side is represented as small a, small b, and small c. So the question arises, sir, how you know and when we have to connect which wire with which wire? Before going to the connection, first of all, we need to find the polarities of the windings on HV and LV side. And these polarities are marked in terms of A2, A1, B2, B1, C2, C1, and small c2, C1. Is it okay? Yes, sir. Further, if you observe all the windings of HV side, I have represented same number of turns. So actually, all the HV windings are identical and all the LV windings are identical. So A phase HV, B phase HV, and C phase HV are identical in terms of number of turns, in terms of thickness of wire, in terms of element used for the wire, everything. Yes, sir. Similarly, all the LV sides will have identical configuration as well as they are of identical materials. Is it okay? They are of same material. Is it okay? Yes, sir. And only we need to perform a polarity test in order to connect a three-phase configuration. If we don't know about these polarity, we can't do the connection. It's a single unit of a three-phase transformer bank. This entire unit is in one container. In case of a oil-filled transformer. Is it okay? Yes, sir. So once the connection is designed, we can't change the connection. Once the connection is designed, we can't change the connection. In case if any one of the transformer get faulted, then the entire unit is unable to process, unable to work, or unable to transfer power. Is it okay? Yes, sir. There is one more way to connect three-phase transformer desired connection, that is called as bank of three single-phase transformer. Suppose we have identical three transformers A, B, and C. All these transformers are identical in every respect. They are identical in every respect. Is it okay? Yes, sir. A, B, and C are identical in every respect. Yes, sir. Now please observe. After performing polarity test, we know how to perform polarity test. After performing polarity test, I am marking one transformer as a transformer and I am marking A2, A1. Similarly, a B transformer, I am marking induced DMF as B2, B1. Okay, yes, sir. And C, I am representing C2, C1, small c2, C1. So after performing polarity test, we know about the terminals A2, A1, B2, B1, C2, C1. Capital A2, A1, capital B2, B1, capital C2, C1. If I am interested to connect the desired connection, that is a star star 0 connection, then I can short A1, B1, C1 together and our neutral will be provided. And similarly, on LV side also, I am going to short small a1, b1 and c1. Please observe. And a neutral is available here. Is it okay? Yes, sir. The output terminals on HV side is A phase, B phase and C phase. And on LV side is A phase, B phase and C phase. So this is how we can connect three single phase transformer to work as a three phase transformer. This is also called as a bank of three single phase transformer connected as a three phase transformer. This connection is exactly same as the previous one. I have represented a star star 0 connection. Later on we are going to know what is a star star 0. So this is a desired connection. So either we can go by the single unit of a 3-phase transformer, or we can go by a 3 single phase transformer banks connected as a 3-phase transformer. Is it okay? Yes, sir. Once this one single unit is designed, you can't change the connection, and in case if it gets damaged, if any winding of the transformer get damaged, your transformer need to be repaired again. Yes, sir. However, when we talk about a 3 single phase transformer, there is one great advantage. In case if one of the transformer will get damaged, then we can connect the remaining 2 transformer in a open delta configuration to feed reduced capacity 3-phase load. So it means just with a 2 transformer we are capable to deliver 3-phase supply. Is it okay? Yes, sir. One other thing, in case of a bank of 3 single phase transformer, the spare part management is cheaper. Spare part management is cheaper means if we have 3 transformer, I can, instead of purchasing 3 identical transformer, I may purchase 4 identical transformer. Let us suppose if one transformer get faulted, then the extra transformer that I have, I can put it here. So the supply, or you can say reliability of the supply, gets improved. So in order to improve the reliability of the supply, this is more preferable. One more thing, a single unit is quite difficult to transport, especially in hilly areas, because the size of the transformer itself is bigger than the trucks. It is quite difficult to fix them in a hilly areas, and hilly areas are the base generating station area. So all the powers are coming from the base power plant. Maximum portion of the power is coming from the base power plant. There we need a maximum ratings transformer. Is it okay? Yes, sir. Onto the load side, where the transportation is not a big challenge, there also we will prefer, when we talk about very high rating 3-phase transformer, then we will prefer to go with a 3 single phase transformer connected as a 3-phase transformer. Is it okay? Yes, sir. Because it gives a freedom to connect in a desired connection, or in case if one transformer get damaged, then also with the 2 transformers connected in open delta, the configuration is capable to deliver 3-phase power. So reliability of the supply improves. Are you able to get the parts up to this? Are you able to get all these things? Please tell me now. Now you are able to understand what is the bank of 3 single phase transformer and what is a single unit of 3-phase transformer. Yes, sir. Sir, we are interested to know about the vector groups now. Let us talk about the transformer vector groups, and we also learn how to connect the transformer in a desired connection. Okay, please write down 3-phase transformer vector groups or 3-phase transformer phasor groups. Basically it's a phasor group, but in some of the books it is represented as a vector group. So 3-phase transformer phasor groups. Please observe. First is group 1. Group 1 is your 0-degree group. Group 1 is called as a 0-degree group. And in a 0-degree group, the possible connections are. Let me write it again. I think it will be a very lighter. So, in a 0-degree phasor group, the possible connections are star star 0 and delta delta 0 connection. In a 180-degree phasor group, the possible connections are star star 6 and delta delta 6. Have you ever studied all these things? Please, in college, last year preparation, or during job, anywhere, have you learned about these connections? Do you know the name? Do you know the names? Star star 0, star star 6. Do you know the name? During your industrial training, do you know the name? Have you ever seen the name star star 0, star delta 1, delta star 1, then star delta 11 and delta star 11? No? Okay. Okay, now please observe. Now please observe. First of all, we try to understand what are the phasor groups. Later on, we discuss why we need to understand the phasor group. Okay. Yes, sir. Now please see. So types of groups are group 1, group 2, group 3, group 4. 0 degree, 180 degree lag, 180 degree, 30 degree lag, 30 degree lead. Possible normal connections star star 0, delta delta 0, star star 6 in 180 degree phasor group, delta delta 6, 30 degree lag phasor group, star delta 1, delta star 1, and 30 degree lead phasor group, star delta 11, delta star 11. There are some special connections also. These special connections are called as a zigzag connection, in which secondary side of the transformer will have two equal portions and they are connected in a zigzag star manner. So the special connection for 0 degree group phasor group is delta star zigzag connection. 180 degree phasor group is delta star zigzag connection. 30 degree lag phasor group is star star zigzag connection, and 30 degree lead phasor group is star star zigzag connection. Please note down. G3 used for distribution transformer, sir. No. Actually, you can use G3 or G4 for a distribution transformer or for a power transformer. There is a reason behind, in our country, there is a reason behind selection of the star delta 1. The delta star 1, star delta 1, which we are going to use for the distribution, we will come to know later on. Once we know about the insulation level desired for delta and insulation level desired for star, as well as other requirements like harmonics. So after harmonic concept, you came to the information that delta star 1 and delta star 11 is a preferable connections for distribution transformer. Star delta is not preferred. Now let's have a discussion. Please see. Now I am going to explain how to perform a connection of 3 single phase transformer in your desired phasor group, or a single unit of 3 phase transformer windings in your desired phasor group. For that, we are going to follow some steps. Okay. So those steps I am going to write here. Okay. Yes, sir. Now please observe. Suppose we have a symbol star delta 1. So what is this star delta 1 denotes? What this star delta 1 denotes? Star delta 1 denotes HV side is in star. HV side is in star. LV side is in delta. One O clock position. Is it okay? No, sir. We are unable to understand this. HV side is in star, LV side is in delta, and 1 o'clock position. See, HV and LV line to line voltages are being displaced in time. So engineers thought, why not to represent in a clock? When voltages are being displaced in time, why not represent in a clock? Okay. So it's a clock representation. Please observe here. We all know about 12 o'clock. We all know about 3 o'clock, 6 o'clock and 9 o'clock. We all know about 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, 6, 7 o'clock, 8 o'clock, 9, 10 o'clock and 11 o'clock. Yes, sir. A clock contains 2 different handles. One is called as a minute handle, another one is called as a hour hand or handle, whatever you want you can say. So sir, minute 1 is lengthwise minute 1 is longer and hour hand is shorter. Minute hand will have more length compared to hour length. Yes, sir. So this minute length is used to define high voltage, and that always placed at 12 o'clock position. Hour position is defining LV side. We all know that the angle between 1 o'clock and 12 o'clock. So the angle between 1 o'clock and 12 o'clock is 30 degree. So this indicates LV side voltage lags HV side voltage by 30 degree. But a student get confused by observing this. They thought that the voltage difference between phase to phase, but that is not HV side phase voltage and LV side phase voltage. Basically, in a clock, if I am representing 12 o'clock and 1 o'clock is the LV position and 1 o'clock is the LV position, we have HV position and LV position, say 1 o'clock. So it basically indicates high voltage side, high voltage line to line, or better to write, HV side is always on 12 o'clock position. So you can write low voltage line to line, low voltage line to line, low voltage line to line is 30 degree lagging from line to line voltage on HV side. LV side line to line voltage. Please, I'm sorry for this cutting. I'm sorry for this change. LV side line to line. LV side line to line voltage is 30 degree lagging in a time from HV side line to line voltage. Is it okay? Yes, sir. So which slide? Now please observe here. Actually, I have represented. I am visible to you? Okay. Actually, I have represented star delta 1. So star delta 1 indicates HV side is in star. If you observe, the star is capital Y and delta is small d. So HV side is in star, LV side is in delta, and 1 represent 1 o'clock position of LV side. Always on clock, LV side position is represented. So 1 o'clock is the position of LV side. HV side is always at 12 o'clock position. So this represent in a time LV side and HV side are displaced by 30 degree. Which voltage is displaced? Sir, LV line to line voltage is 30 degree lagging from HV line to line voltage, because in time phasor rotates in anti-clockwise direction. So in time phasor, if the time phasor rotates in anti-clockwise direction, then in time phasor, first phase that comes in front of our eye is HV side, and after 30 degree LV side will come in front of our eye. So it means LV side is getting maximum after 30 degree from HV side. So this is line to line voltage. Always remember, only line to line voltage difference is represented, because phase voltages are, induced EMFs are always in same phase. From day one I am saying induced EMFs are always in same phase because they are due to the same flux. This displacement is between line to line voltage. This displacement is in between line to line voltage. Now come to the second point. Please observe. What is second point, sir? Only for reference, take high voltage line to neutral at 12 o'clock position. Only for reference, in order to find out which terminals we need to connect for our desired connection. Only for that purpose, only for that reference purpose, I am going to take high voltage line to neutral placed at 12 o'clock position. So please write down. For reference, take high voltage line to neutral at 12 o'clock position. Next point. HV side A phase is brought out from terminal A2. It is not mandatory. You can take it out from A1 or A2. Just for the reference, if we are going to say a same language, then only we can communicate. So for that purpose, I am just giving one fixed notation. Okay? Yes, sir. So both of us are able to understand in a same way. Okay? So for that purpose, I am just taking a reference. So always take HV side A phase is brought out from terminal A2. Just write down. Third, keep the phase sequence ABC. Either you can take ABC or ACB. So I am suggesting always we are going to keep the phase sequence ABC. We are going to keep the phase sequence ABC. Is it okay? Yes, sir. Now, very important point. Parallel lines always represent in phase parameters. Parallel line always represent in phase parameter. Finally, last one. Induced EMFs are always in the same phase. Always remember this. Induced EMFs are always in a same phase. So induced EMF on HV and LV windings are always in same phase. It means induced EMF on HV side is in phase with induced EMF on LV side. So the line to neutral voltages on HV and LV sides are going to be in same phase. Only for the reference, you have represented high voltage line to neutral at 12 o'clock. Is it okay? Okay. Let's discuss the first case. In order to understand 100% about the connections, we must need to listen 3 cases first. 3 cases. So you need to keep patience for 3 cases. Okay. If you are getting just 10%, then sufficient. Up to 3 cases. On third case, you are going to get 100%. Okay. And from fourth onward, you can construct a 3-phase transformer by your own. So please observe. You can design a connection, desired connection by your own. Please observe first case, case 1. Case 1. I am going with a star-star 0 connection. Okay. So you need to keep patience for 3 different connections. Let's first connection wise, this is a star-star 0 connection. Okay, sir. So it means HV is in star, LV is in star, and HV line to line voltage and LV line to line voltages are in same phase. So I want to design a star-star 0 connection 3-phase transformer. Star-star 0 connected 3-phase transformer means HV side line to line voltage and LV side line to line voltage should be 0 degree displaced. So now please observe here. If this will be your HV side voltage VAB, then line to line voltage, then LV side line to line voltage must also be in the same phase. Its magnitude may be different, but LV side line to line voltage must be in same phase with HV side line to line voltage. Is it okay? Only for the reference, because we know that we have to create a connection where line to line HV and line to line LV are in same phase. Only for the reference, I am considering let line to neutral of HV side line to neutral of HV side at 12 o'clock position. So let line to neutral on HV side at 12 o'clock position. Is it okay? Yes, sir. 0 degree. 0 degree displaced means 0 time. What is 0 time, sir? 0 time is same as the 12 o'clock, sir. 0 time means 12 o'clock, sir. So HV is always kept at 12 o'clock position. I have represented here. For reference, take high voltage line to neutral at 12 o'clock. So HV I am going to put always on 12 o'clock. What about LV? LV is represented by this clock position. So 0 time means 0 time means same as 12 o'clock. It means LV is also at the same HV. Okay? Yes, sir. Now let's consider a neutral here. Let's consider a neutral here. In a space, I am considering a neutral. Okay? HV side we have to construct in star. So it means A phase voltage, B phase voltage and C phase voltage are being displaced in time by 120 degree. So these voltages are being displaced in time by 120 degree. A phase, B phase and C phase voltages are being displaced in time by 120 degree. We have to keep the phase sequence as per the node point. We have to keep the phase sequence ABC. We are always going to keep the phase sequence ABC. So I am writing A here, B here and C here. Now please observe here. HV side A phase is brought out from terminal A2. So we have two terminals. In a winding, we have two terminals. Already we have observed A2 and A1. We have two different terminals for A phase, A2 and A1 on HV side. Similarly, A2 and A1 on LV side. So out of A2 and A1, from which terminal you are going to connect the supply or the load? It means the terminal which we are going to take out. That is called as a A2 terminal here. So I am taking out, A phase is taken out from A2 terminal. Similarly, B phase is taken out from B2 terminal and C phase is taken out from C2 terminal. What is the phase sequencer? A phase, B phase and C phase. Now please observe. Again the same neutral I am representing here. Again the same neutral I am representing here. Okay, sir. Now please observe. Again the same neutral I am representing here. Induced DMFs are always in same phase. Yes, sir. And parallel line represent in phase parameter. So I am going to represent a line which is parallel to A phase. Again, please observe. I am representing a neutral here. HV we are getting here. LV we are getting here. So A phase we are getting here, and A phase we are going to obtain from A phase only. Induced DMF on HV and LV side are in same phase. So I am representing a line which is parallel to A phase. This line is parallel to A phase only and only if arrow tip terminal is A2 and arrow tail terminal is A1. In case I am going to represent opposite, then they are being 180 degree displaced, because we know that the suffix 2 are represented by dot and the suffix 1 are represented by without dot terminal, and dot terminals are a same polarity terminals. Is it okay? Yes, sir. So if I have represented the arrow tip at 2, then arrow tip is at 2 only. This line is in parallel with this line only if this one is A2 and this one is A1. LV side is also in star and all the phases are identical. So I am drawing a line which is equal in magnitude to A2 A1, but 120 degree from A2 A1. Then again 120 degree from A2 A1 I am drawing C2 C1. Now please observe. We have to identify. Now this is a star. Okay. We have to identify this line is in parallel to. This line is in parallel to which line? This line is in parallel to B line. When this line is said to be in parallel to B line, only if this is B2 and this is B1. Great, sir. When this line is in parallel to C line, this line is in parallel to C line only if this is C2 and this is C1. It can be observed here, A phase is taken out from A2 terminal on LV side. So we have to keep the symmetry. B phase must be taken out from B2 terminal. and C phase must be taken out from C2 terminal. Okay, sir. Now, please observe. Please observe. So we have HV side and LV side phasor. Now, please observe. Sir, you said the time displacement between line to line on HV side and line to line on LV side is 0 degree. Kindly show me the line to line voltages, sir. Please observe here. What is line to line voltage? Let us talk about VAB. What is VAB, sir? VA minus VB. What is VA minus VB, sir? We can go in this way, sir. VA minus VB. And what is VA minus VB, sir? VA minus VB can be represented here, sir. This is your line to line voltage VA minus VB, sir. This is your line to line voltage, sir. VA minus VB. Can I represent in this way? Can I represent in this way? Yes, sir. This is your line to line voltage VA minus VB. What is this angle? 60 degree. What is this angle? Sir, 30 degree. Is it okay? And magnitude of VAB is equals to, sir, if VA, VB and VC are equal in magnitude, then VAB will be equals to √3 times of the phase voltage. Already we have observed this. You can represent this line here, or you can represent this line here. Can I represent this line here also? Yes, sir. You can represent the line either here, or you may represent the line here. Both the lines are parallel lines. Okay? Yes, sir. So the same line I can represent here with the same magnitude and the same direction. This line is called as VAB line. I have represented this line from B to A. I have remarked the line from B to A, VAB, and it is 30 degree from B phase. Since it is 30 degree from minus B dash, it means 30 degree from B phase. Is it okay? Yes, sir. Great, sir. Is it okay? Yes, sir. So line to line voltages can be represented here as VAB, VBC or VCA. But I am only representing one line to line voltage, because the nature of one line to line voltage, the relation between line to line voltage on HV side and LV side of one line to line will same for all other. Okay? Yes, sir. Similarly, one can say, sir, what is VAB small? VAB small can be represented here VA minus VB. Yes, sir. What is VA minus VB, sir? VA minus VB can be represented here in this way, sir. VAB. Can I represent in this way? Yes, sir. Can I represent in this way? Please tell me. Yes, sir. Please tell me. Yes, sir. Sir, this is at an angle 30 degree from here. 60 degree this entire one. Yes, sir. So same VAB can be represented. Same VAB can be represented, sir. Same VAB can be represented here, sir. Is it okay? Yes, sir. Sir, this is your B to A, VAB small. Now please observe, we have two phasor, VAB capital and VAB small. If the two phasors are in same phase, then we can represent them on a common reference point. Yes, sir. So if we are going to represent them on a common reference point, what is the time angle difference between capital VAB and small VAB? 0 degree, sir. What is the time angle difference between small VAB and capital VAB? 0 degree, sir. It means small VAB is 0 degree displaced, from capital VAB. Small VAB is 0 degree displaced from capital VAB. Is it okay? Yes, sir. I'm interested to perform a connection. So how to perform a connection? Let us suppose we have a 3-winding transformer, or we may have a 3-winding three different transformers. Suppose we have 3 different transformers. This is transformer A. Now I'm going to show you transformer B and transformer C. So HV and LV side of transformer A, HV and LV side of transformer B, and HV and LV side of transformer C. So we have A2 A1, we have a B2 B1 and C2 C1. We have a small A2 A1, small B2 B1 and a small C2 C1. We know how to find the dot. Yes, sir. So after performing polarity test, we can calculate. We know about the dots. Once we know about the dots, then our phasor suggests us how to make a desired connection. Sir, phasor suggests A1, B1, C1 are shorted. So I'm using one external wire to short A1, B1, C1, and we have a neutral. The port A is available for A phase, port B2 is available for B phase, and the terminal C2 is available for C phase. On LV side, it can be observed that A1, B1, C1 need to be shorted. So I'm going to short A1, B1, C1, and we have neutral. This is A phase, B phase, and C phase. Is it okay? Yes, sir. Every HV turns are identical. So all HV turns will have total number of turns NHV, and all LV will have total number of turns NLV. Yes, sir. Yes, sir. Hoping up to this part everything is clear? No, sir. We are presently at 0. We are presently 0 for this 3-phase connection. No issue. Up to this part, hoping everything is clear? Nothing is clear, sir. We just know about the 3-phase system. We are waiting to understand about 3-phase transformer connection. Thank you, everyone. Thank you, everyone.